So we found relative maximums and relative minimums. But what if I want to find the absolute maximum and the absolute minimum my function takes on? We're going to look at what happens over a closed bounded region. Remember back in Calc 1, you were asked to find the absolute maximum and minimum over a closed interval, and it did exist. You checked any critical points within the interval, and then you check the endpoints, because if your function ends at the endpoints, technically those are critical points also. So you check all the critical points. The biggest one was your maximum and the smallest one was your minimum. Well, how is this going to be different in 3 space? Very similar. Suppose we have Maleficent's hat again. I can see there's an absolute maximums and the minimums. It just keeps going on and on forever. But so this does not have an absolute minimum. But if I look at it over a closed region, I can see there is a minimum. So just like in 2 space, we know that if f is continuous on a closed bounded set, then f has an absolute maximum value and an absolute minimum value on D. But how do we find them? A lot like the way we did it in Calc 1. You're going to find the critical points of f that are inside D, and then find the value of the function at those points. You will also find the extreme values of f on the boundary of D. You compare the values, the biggest is the maximum, and the smallest is the minimum. So let's look at an example. Suppose I have this function, and my region is x is between 0 and 4, and y is between 0 and 2. So it looks something like this. I'm going to first look for critical points. So my partial with respect to x is 2x minus 2y minus 4 equals 0. And my partial with respect to y is negative 2x plus 8y minus 2. If I add the 2 equations, I get 6y minus 6 equals 0. So I know my y equals 1. Plugging that back into one of my equations, I find that x is equal to 3. So I want to find the value of the function at the point 3, 1. So plug and chug, and I get 17. Now what we have to do is check along the boundary. First, I'm going to check the corners, because I know those are all critical points. So f of 3, 1 we know is 17. We have f of 0, 0 is 24. F of 4, 0 is 24 also. F of 4, 2 is 20. And f of 0, 2 is 36. Okay, so now we're going to look at the 4 sides. The line L1 is y equals 0. So if I make y equals 0, my function now looks like this. X squared minus 4x plus 24. Now I take the derivative of that, set it equal to 0, and solve. I get x equals 2. So I have the point 2, 0, because I already said that y equals 0. I plug that into the function, and I get a 20. Let's look at the second line. This is a line where x equals 4. Plug that into your function. Get 4y squared minus 10y plus 24. We take the derivative, set it equals 0, and solve. If y equals 5/4 and x equals 4, the value of my function at that point is 17.75. Next line. Let's say we are looking at y equals 2. Plug it in, take the derivative, set it equals 0, and solve. X is 4, y is 2, plug it into my function, and I get 20. Last line, I have x equals 0. Plug it in, take the derivative with respect to y, set it equal to 0, solve. I get y equals 1/4. So now I have the point 0, 1/4. I have one more value to look at. So let's look at this. We have a whole bunch of points to look at. And comparing the values, so I see that the absolute maximum is 36 and it occurs at the point 0, 2. The absolute minimum value is 17 and it occurs at 3, 1. Let's try one with a little bit grosser region. Suppose I have the function x squared plus y squared minus 2x, and my region is the triangular region with the vertices 2, 0, 0, 2, 0, negative 1. Notice what these lines are. They're not horizontal and vertical, all horizontal or vertical lines. So let's go ahead and knock those out. I know L1 is the line x equals 0. L2 has a slope of negative 1 and it goes through 2. So it's the line y equals 2 minus x. And L3 is the line x minus 2. So critical points first. The derivative with respect to x is 2x minus 2. Set equal to 0, solve. I get x equals 1. Derivative with respect to y is 2y. Easy peasy. That gives me y equals 0. So my critical point is 1, 0. I plug it into the function and I get negative 1. I'm not going to do that funky movie stuff anymore. That was a pain in the butt. But it looked cool. So that's my critical point. Now let's check the corners. I have 3 corners. Checking all those values, I get a 0 and 2 4s. Next, let's try line 1. Line 1 is where x equals 0. I plug that in, I get y squared. Take the derivative, set it equals 0, I get y equals 0. So the point 0, 0 gives me a 0. Boy, lots of zeros. Next, let's look at line 2. At line 2, my y is 2 minus x. So I'm plugging in 2 minus x for y. I plug that into my function up here above, and then I simplified. I got 2x squared minus 6x plus 4. Take the derivative, set it equals 0, solve for x. If x is 3/2 and y is 2 minus x, then y is equal to 1/2. And I plug that into my function, and I get a negative 1/2. Lastly, let's try line 3. Line 3, my y is equal to x minus 2. I plug that into the function. I get the same polynomial because if you notice in the original function, y is squared. So it doesn't really matter if you put in a positive number or a negative positive value or the same negative value, you will get the same function. And x minus 2 is just the negation of 2 minus x. Anyway, I digress. Taking the derivative, set equals 0. Again, we get 3/2, but this time my y is x minus 2, so that becomes negative 1/2. And when I plug it into the function, I get yet another negative 1/2. So here are my values. Let's compare. I have a minimum value of negative 1, which occurs at 1, 0. I have a maximum value of 4, which occurs both at 0, 2 and 0, negative 2. So we have found the absolute maximum and the absolute minimum of this function over the region D. So let's look at the big picture. What do? You really should try to sketch the region so you see what's going on and see what the corners are and what the edges are. You want to find all the critical points of f in D and plug them into the function. You want to find the extreme values of the function on the boundary of D. Then you compare the values. Biggest is the maximum and the smallest is the minimum. It's kind of long and tedious, but that's all there is to it.